But I guess we should start. So welcome to the presentation on the year 2038 problem. We are going to talk today about a few things. First, what the underlying problem is, and then what the general approach is that we are picking to solve the problem in Linux, and then we are going to look at specific parts of the kernel and user space of what approaches we're taking there to address individual problems. And I'm doing this presentation together with my intern, Tina Ruchandanit. It's her first time presenting at a conference, so please welcome Tina. She's talking about the first about the problem that we're facing.
Thank you, everyone. Hello, everyone. I'm Tina, and I'm a GNOME OPW kernel intern. Well, most of you might not be aware about what OPW is. OPW is an outreach program for women. It is basically a program to encourage a woman to take active part in the open source community. So I'm an intern of that. Now, moving on to the problem. Understanding the problem. Let's have a fun exercise here. Most of you have Android phones. So if you open your Android phones and try to set your date to future, say 2040, so what you will observe is that the date doesn't go beyond the 2037. Strange, isn't it? So, going on to the 2038 issue. This is what the problem is. It is similar to the 2000K problem, which Windows had occurred and many other problems were there. So, oops.
Sorry.
So what is exactly 2038 issue? So the representation of time in a Linux is basically based on the time structure, that is time underscore t, which is a 32-bit signed integer. Now this time underscore t represents from seconds that has been elapsed since a date, which is also known as the epoch or the starting point of the Linux. I mean the time, that is the 1970 around. So as in the Linux we have negative timers as well. So there are negative time and as plus as a positive. So in the total all, the time is represented from the 1901 to 2038 in overall 136 years. So, but we have 23 years. Why are we worrying about it? So the significant portion of this problem is that the internal timers, when they are set beyond the 2038, they won't fire. And so the problem is that with the kernel timers. The next one.
Yep. You want this one?
So the problem with that is now the 32-bit ARM systems that has been deployed are using this time underscore t representation. So they may have 23 years of lifespan until 2038. So let's go with the car example. This car is not a classic car, so maybe you'll not be owning in the future. But if we consider a Lamborghini car, which is actually a dream of most of the people, so in that Lamborghini car you have a dash system, that is a clock, which is manufactured by a very famous company called Breguet system. So that clock will not work in 2038, but the solution is that you can actually pick it out and hand wind it. So luckily that's okay. So the next. So talking about the future present cars, that is a Tesla. So Tesla is a 32-bit fully functioned car, and it's actually inexpensive. So in being a 32-bit ARM structure, it is going to be terminally broken in 2038. So yeah,
it's running a Tegra
until and unless you get a battery replacement every 2-3 years. So other long deployment file systems. So moving on to the Android phones and cars, we can replace it anytime, it's our own wish. But the systems which are using 32-bit ARMs, like the defense systems, we have medical systems, and there are many more. For example, wireless. They may be they get terminally broken in this year 2038. As the embedded processor devices gain more power, this may cause a problem in the future. Find the solution. That Arnd will take.
Okay, so as we've seen, we have systems that we can't get rid of. We will keep deploying 32-bit systems. Not everybody is moving to 64-bit systems soon enough that they will die out by the time we have the problem. And even on 64-bit systems, people are running 32-bit applications, and they are equally broken. So even if your hardware is all fine, the kernel is all fine, the kernel is still broken. Sorry, the user space is still broken. So let's look at what other systems have done about this problem in the past. Recently, OpenBSD changed this. The starting situation on OpenBSD was a little bit different, because even on 64-bit OpenBSD systems, they had 32-bit time T, whereas on Linux we have 64-bit systems already have 64-bit time T that can last for billions of years. Okay, please go ahead. So what they did in OpenBSD was to recompile everything, just changing the type def for time T. They rebuilt the kernel, rebuilt the C libraries, rebuilt all of user space, basically making everything incompatible with the previous version. But they could do that because they didn't have a large user base, and they are shipping the whole operating system as one source tree and one set of binaries. So they were able to do it with this change all at once. But still, if you have an old OpenBSD application, it definitely stops working at this point. NetBSD has taken a different approach. A couple years earlier already, they were in the same starting situation as OpenBSD, but they have chosen to keep the compatibility at the library level. So NetBSD also recompiled their kernel and their C library using a 64-bit time T on all systems. But instead of breaking existing applications, they have chosen to keep the binary interface between the application and the C library. So they can run old and new applications. Whenever you rebuild something on NetBSD, you will get a 64-bit time T and it will keep working beyond 2038. So they have a gradual expiry of the old application. Whenever it gets rebuilt, it's fine. Well, unfortunately, we can't do that on Linux either. First of all, the C library is separate from the kernel. We take big pride in being able to run the latest kernel with a 10-year-old distribution with the old C library, and we want to keep that working. And also, lots of people have different C libraries. You have the embedded systems that use UClibc or newlib or something like that, and you have the desktop distros that use something like glibc. So they're just separate code bases, and we have to take them one at a time. So what we do in Linux is we fix the kernel first, leaving all the interfaces to the C library intact, which is a much harder approach than what I did for the BSD kernels. But it's the only way we can keep existing user space working while at the same time addressing this problem. And then for each C library, they will have to come up with their own solution for the problem for user space. And that's just for building things. The situation is slightly different between rebuilding a new application, because that depends on what C library you have, and running an application that has already been built. We want to add the interfaces for running 64-bit time T applications. But we will probably make optional the interfaces for running an old application, so that you can build a kernel that only supports new applications if you want to be sure that everything breaks now instead of breaking 2038. That's a very important scenario for embedded systems. You don't want to be surprised by breaking things. If you and be able to do all the validation testing on the system, make sure it runs now, and it will keep running that way. What does it mean in the kernel? Now we have, we did a survey early on. There's hundreds of files using time t, struct time spec, struct time val, and other structures embedding a time t. These are all broken. We have a couple dozen system calls where the time t is passed from user space into kernel. For each of those system calls, we will have to come up with a way to make the old one keep working and have a new one that will work across 2038. Then we have device drivers, and finally we have data structures that are used to other components outside of the kernel, either sent over network protocols, and every operating system will have those problems. And also, the same thing is true for file systems. If you're storing a timestamp for a file on a 32-bit integer, it will overrun and will break in 2038. So we have to fix those as well. And even if we do those, that's just the kernel. So there's still plenty of applications that do not use time t. So even rebuilding those applications, you still have problems if they are written in a way that's not portable, if they just store a time t value in an unsigned int variable or signed int or something like that. Or we still rely on the glibc people. So what we are looking at is basically just the kernel for now. And once we are done, we can hand over to the toolchain team. What we've been done so far, so John has done a lot of work together with Thomas Gleiks now on getting the timekeeping code converted to using 64-bit time t. That was the main first stepping stone so that we can actually start converting the device drivers. Because before, we did have the 32-bit kernel didn't have the concept of reading the time in a way that will keep working. And then from there, he's working his way out. I've started looking at system calls, trying to work my way in from the user space interfaces to the point where we meet in the middle. And then in OPW, so Tina is working on this full time. She's the first person to address this problem full time in Linux. In the application phase for OPW, we had a number of other women sending patches addressing small driver issues one at a time. And that's been very good. We've had some other volunteers step in. Junyan from Linaro has done some work, and several others have also sent individual patches.
Zunli as well. Zunli? Zunli?
Yes, yes. Sorry, I didn't. So we've done about 10% of the files, but most of them were the easy ones, and we'll probably leave the harder ones for later. So and now I hand over again for a short look at what it takes to convert one device driver.
Thank you, Arnd. So, fixing driver internals. This is one of the patch I did for my OPW application, where I was handling a normal cleanup patch for a small driver. The driver is the sound, and I'm handling this, the ES1968.C. Now if you have a look at the code, you'll see there is a stop time will and there is a start time and stop time. Basically, giving you an idea what is happening in the code is that we are getting two times. One is the start time and the stop time from the get time of the day, and that is returning us the present time and the after time. It computes the difference between these two, and it passes to the t variable, again a 32-bit variable. It is multiplied with the 1 million to get again in a milliseconds. The milliseconds is used to check whether the start time is greater than the stop time, and so the driver proceeds on further implications. Now the problem here. So time world, being a 32-bit signed integer, will overflow in 2038, as well as its functions, that is the do get time of day and do get time of day ampersand stop time, will also have the same fate. So we need to try to remove this. So the basic solution is we can either replace it with the 3-4 structures that we have, 64-bit resolution, nanoseconds resolution, that is time spec 64, k time underscore t, as well as time, there's one more. So first I tried as the time spec 64. So an easy replacement, so just we are directly replacing the time spec 64. So in that was using the milliseconds resolution, Here we are getting a nanoseconds resolution. So, but the problem here is, if you look at the t variable, there the t variable was multiplying by 1 million, and here the t is getting multiplied by 1 billion. So the t being a 32-bit variable, it can cause an overflow in 2038.
Well,
Might
after,
be, it's
after
possible.
4 seconds.
Yeah, after the first 2 seconds. So, how to solve this thing? So another function we could use is the k-time underscore t. Now the benefit of using the k-time underscore t is that it gives us a nanosecond resolution, but it has an predefined some functions like k-time get and k-time underscore us underscore delta, which is directly getting us the subtraction of the start time and the stop time in nanoseconds resolution. So there we need to convert the 2t into the nanosecond. Here we are getting the direct replacement of nanoseconds. So it's an efficient, safe, and easy to use. And the another benefit is that the number of lines of codes there was around 9, and here it's getting reduced to 3. So that's another benefit. So the next is the system calls. Again, a trivial solution.
Thank you. So system calls is by far the hardest part that we have to solve. Well, the second hardest part, I should say. This is the simplest system call I could find that has the problem today. System call is an interface from user space to kernel, so we don't see the regular C calling conventions. What we have in user space instead is we know a number that is defined, in this case number 13 is the time system call that returns the number of seconds since 1970 as a 32-bit value. The C library will use this number, put it in some register, depending on the architecture, and then call into the kernel to get this function call. The kernel enters, it calls an internal function, it stores the value into a user space pointer and returns. That's what the basic system call does. And again, we have the time t that is known to overflow, and we have the get seconds call, which is the kernel internal interface returning a 32-bit value. We have to replace both of these. So what we're going to do is to introduce a new type, kernel time 64t, that is always 64-bit, that is exported to user space. We replace this existing function with this, and we call a kernel internal helper that returns a 64-bit number. The problem with this, of course, is that now we've changed the system call now, and we will break existing applications. So any application that uses the number 13 to call into the kernel expects the old behavior, so we can't use this call with the existing system call number. We have to come up with a new system call number. This would be the next free one at the moment. By the time we get there, it's probably a different number. But for each system call like this, we have to come up with a new number that represents the fixed interface. And then, of course, we have to provide a different function with the old interface. So in this case, we have a different macro for defining compatibility interface. This takes a different type, compat time t. This is already what we use in 64-bit kernels when we are running 32-bit user space applications, which have the same problem already. Like we have 2 implementations of the system call. So in this case, we have the compat time and the new time with the new number. Compat time gets the old number, so we replace the system call but keep a different version in there for the existing application. And this is the current definition we have for the time types. So we have an internal kernel time t, and that is defined to time t, which is the type that normal user space uses. And this is what what we're planning to add for this case. So there's going to be a configuration symbol that is first of all set by all the 64-bit architectures. If this is set, we have the new kernel time t and we have the compat time t. And this will work unchanged on 64-bit architectures with a new definition. if the compare time configuration symbol is not set, we would have a temporary definition that basically defines the new type to the old type, which is 32-bit. That's just a transitionary definition. We will do this for all the system calls we have, and then convert all the 32-bit architectures one at a time to use the new system call numbers, add the compatibility handler, and set this macro. Once they're all converted, we get to the next stage where we remove this fake definition. We just unconditionally define kernel times 64T, and we use this for the correct handler. We use this only for compatibility with old applications, both on 32 and 64-bit systems, where the latter ones emulate old 32-bit user space. I hope I wasn't blowing your mind with this. Yeah, the system calls are very hard. So let's talk a bit about user space for a moment. This can be a lot easier. First of all, the most interesting aspect here are embedded distros, because those are the ones that are producing systems that will be deployed for the next 10 years and may have a lifetime of 15, 20 years after that, and will run into this problem. They can, once we have completed the work in the kernel, they can change the C library to use 64-bit timesheet, recompile all their user space, which is the normal model on embedded systems anyway. If you have something like Open Embedded or OpenWRT or BuildRoot, you always build everything from source at once. So you just define this type to match the new definitions in the kernel, recompile everything, and it works. Except for the I/O controls. So I/O control, any application you have that uses I/O control, we have to look at in detail. Because they are defined in various different ways, and some of them work, some of them may not work. And then there's the other problem that I mentioned earlier. When you have an application that does not use timesheet, it doesn't help you to redefine timesheet, you also have to change the source code for your application to either use timesheet or use a 64-bit type. The much harder problem are the standard distributions. So if you take something like Fedora, OpenSUSE, Red Hat Enterprise, Linux, Debian, Ubuntu, any of these, you can't break compatibility. There's no way you can expect users to recompile all their applications. Even if the distro recompiles everything, you still want to run applications that users have already installed locally. So that's not an option. They will want to use the same method as NetBSD for the user space. So the C library will provide old and new symbols, just like the kernel does. We have a second layer of compatibility, and we have to look at one application at a time. We have to recompile them against the new interface, making sure that all the dependencies are already converted first. So this will take time. It will take a lot of effort from developers, mostly in glibc, but also in the distros. It's unclear what distros we will see. So 32-bit distributions like this in 2038, there probably won't be many. There may be Debian. I don't expect any of the other desktop distros to still be around. What we might still see is support for 32-bit applications running on a 64-bit kernel. We have this today. There's something later this week about adding support for 32-bit applications on ARM64 CPUs that don't even have 32-bit instructions, just by running them with a reduced register length. So there's definitely interest, and in some corner cases, that might still be needed even on server systems in a few decades. If you look at mainframes, there are still mainframes running 24-bit code mixed with 31-bit code and 64-bit code on the same machine in modern systems being deployed today. And the 24-bit mode has been deprecated for at least 30 years. I/O control, I mentioned is a big problem. We need to look at each one individually. They're all different. Some of them, most of the IO controls do not pass time values. That's fine. Out of the ones that do, a lot of them will keep working if they were written correctly and the size of the data structure is encoded in the IO control command number. We can just change the driver to accept both the old and the new command, and it will work. A lot of drivers don't do that because they were written before we had standard ways of defining IO controls. Then there are people that define their own structures that don't use time t but still pass a time value. There might be all sorts of other problems. Basically, it's complicated. I could talk for hours just about IO control alone. So we'll leave it at this. If you have specific questions, you can ask me later. And now I'm handing back to Tina for file systems.
Thank you. File systems, most difficult part of my internship. So file systems will, some of the folks have there in the mind that why can't we switch to 64-bit? That is the best possible solution if we don't have bit. Well, I'll show you why 64-bit is not an option. So I have a file system. This is an XFS file system. So what I did is that I am assigning a timestamp to that file system. See the date, that is the Jan 7, 2038 for the future 1, and for future 2 we assign it as 2039 Jan 7. So now when I unmount it and I go for to check its timestamp whether it is the correct one or not by using the ls-lha command, what I observe is here, see, so the root 0 Jan 7 2030 future and the future 2 is 1902 December 2nd. So do you see the change? That is from 2039, it's switching to 1900 time. So that is a proof of the negative kernel timer. So that is what being explained in the file system. And this is a 64-bit system. This is compiled in a 64-bit system. So this is not, 64-bit is not a solution. Except.
Oh. Right. So.
Okay.
Yep.
Fixing file system timestamps. So there are 3 parts of the solution. The first part is I will talk about the first part, that is about the on-the-screen presentation of the file. So what was happening in the previous XFS file was that the file system was writing the time on the disk. So that's why the disk was in the 2038, when we mount it, it will return as a negative value. So this is something that file system code controls. Now, so today the file system uses time spec, that is a 32-bit seconds value, and as a part of the structure that is returning to the disk. So this structure has some padding bytes or the unused bytes, which can be used as an extra byte or you say an epoch. So we can borrow that 1 byte from the unused disk space as a epoch and then compile it with the 32-bit sign time to return another data time. That is, I'll show you in the backup slides. So how it's exactly going. Okay. So now inode operation. The second part of the solution is the inode. So inode is basically using the getAttr and the setAttr callbacks to read-write the files timestamps. Now, one has to be careful here because this has to be changed for the file systems and these calls are very complicated to use. So here's the solution which is given by Arnd, that is using a neat trick which all other file systems can compile while it is being changed. You can ask him in the questions if you have. Next please.
So this is the inode operations is in the file system independent part, so that's common for all the file systems. Interesting part. Yeah.
Now, IOCTL, as Jan discussed, it is again a interface between a user space and kernel space. It is a way for user space to interact with the file design and the descriptor. That is Arnd spoke about the IOCTL command. Now, the solution here is similar to the first part of the solution by using that extra byte and extra bit padding. So what we do here is we assign that extra bit padding. So suppose I have a 2-bit, let's consider a 2-bit signed number. So the 2-bit, the range would be 0 to say 0 to 99. So if I want a 3-bit number, I need to get it one more bit. So I'm using that extra bit and assigning it as an epoch. So that has a 0 to 9 numbers. So what I'm doing is 100 into that epoch plus that number, 2-digit number. So we get a 3-digit number. Is it making sense? Okay. So let's have that slide actually at the end.
Sorry.
Here's the slide. So as I said, suppose we have a 2-digit number, the range is from 0 to 99. Add 1 digit as an epoch or an extender digit. So the epoch is first considered as 0 when we want 2-digit number. Now when the 2-digit number turns 99, we set the value of the epoch as 1. So that would be 100. Then it goes on continue to 100, 199, so on. And as it reaches 199, another epoch digit will be added. That would be 2. So 2 to 299, and so on. We get the true value as 100 into epoch plus a 2-digit value. So we have extended the range. So that is, this concept is being used in the file system, the first portion of the solution and the third portion of the solution, where we assign this epoch a timestamp and we use it as an extra bit or padding to be added to that the same time underscore t. And so we find a solution to that. Any questions?
Question. Yeah. So thank you very much for this. And that's been all of the presentation so far. So questions for either of us?
Since this is actually the Unix time epic, this has been a problem that's been going on for a much longer period of time, and it's probably shared by many more systems than just Linux. And so the question is, have you gone to take a look at how this has been defined by POSIX, or are you working with the POSIX people to work up a standard way that would be reflected across perhaps all of the Unix-like systems?
So there's Peter Enven has been, he's part of the POSIX team, and he's been discussing some aspect of this. In particular, there's a problem with time spec being defined as containing a long instead of containing a time t, which we could redefine. So that's a bit of a problem. We've basically looked at what the other existing Unix systems do, and extending time t to 64-bit is the only approach that we've seen anywhere else for the POSIX APIs. For the file systems, the example that Tina gave is a completely different approach, but since it's local to that file system, we don't care what they use as long as you get a time t representation back to the kernel.
There has been some folks talking about so there have been some folks who have been talking about trying to establish a new time structure standard that would handle a lot of different issues, not just the 2038. My concern with that is that that doesn't address legacy applications, and where we need to be able to provide, a recompile compatibility in order to fix that issue. It's just one of those things where that new time structure may be something we support in the future, but I think we're going to have to support 64-bit time t.
Along the same lines, I know that time is one of the things that drives the virtualization people crazy. And so have you given thought to having virtual machines running on top of these, and how they might be able to, or at least make them aware of this issue going forward, that they may have one system with a virtual machine on top of it that's running another system that has to make all these time T's work together somehow?
To be honest, we haven't spent a lot of time talking about these, but really the problems with virtual machines and time are, as far as I can imagine, mostly unrelated to this, because it's more related to the passing of time, not the absolute value. The only time where we need the absolute value is when accessing the real time, when the virtual machine starts up and it wants to know what time it started at. From going on from there, it's about making sure the time is actually synchronized and passing at the same rate, which is a hard problem, but this one doesn't make it harder as far as I can tell. Any other questions? Yes.
You said that the problem is getting worse because people keep adding code that use this track time bar and stuff like that. Have you considered putting something as checkpads to prevent people, you know, when they submit a patch that's something like that, I don't know, a warning or something saying you probably shouldn't be doing this?
That sounds like a good idea.
Yeah, that sounds like a good idea. I don't think I said that it's getting worse. So I don't think we're adding these at a high rate. I looked at the number of files, how much time T we use in the kernel, and it's been between 750 and 800 files for the past few years, and now we've brought it down to around 720 files. So we've got a handle on those. Using checkpatch is probably a good idea, but it's not super urgent, I think.
I've actually been surprised since the time T64 showed up in 3.17. We've actually seen a number of patches already submitted that totally unrelated, just doing their own thing, that are already using it. So it's one of those things where the adoption's kind of being picked up by folks who are doing active development now, faster than I expected. So.
And most users are really trivial in device drivers. As the first example of the sound driver, it's very easy to convert. When we're reviewing a driver, you will pick that up very easily.
So I expect that the compatibility for old application is going to survive 2038. So what's the strategy for the old legacy representation of time T when that deadline is passed?
We've been under the assumption that it's not going to survive.
Yeah.
If you have an application that has been built already against a 32-bit time T, or that will be built against 32-bit time T over the next few years, it is broken in 2038. It has to be rebuilt, and that's why we have to fix it now.
You need to do some mitigation. Like clamping it, the value, instead of wrapping it, or something like that.
I don't know.
So far, the approach has, like, my approach on this is we should break them as early as possible. We should make it possible to, as I said, build a kernel that does not have any of the compatibility code, so the application will be broken unless you explicitly turn it on. You get a warning, you know that it's broken now, and we tell everybody who's deploying an embedded system to turn on that option to catch that code, so it breaks now and they don't deploy it.
Okay, so then it's a matter of sending them a kill signal if they use the old system call, something like that.
Well, it would. There are various ways of how we could enforce it. One way would be to have a one-on-ones that prints the backtrace in the kernel of the first user of an interface that we know is going to be broken. The final step would be, like, the strictest way I would do it is just return enosys from all the system calls that are known to be broken.
Or kill it. Yeah, I mean,
Yeah.
I would think that would probably be the best.
Not define the IO control numbers or not even the system call numbers, whatever.
There will be the case of a number of applications that don't care about absolute time and are using 32-bit time values for relative time. And in those cases, they can handle the overflow, and they'll be okay. It's just a matter that, you know, anything that does want to have absolute time, there's nothing we can do. I mean, it's the end of the road. It's right there. So.
For file systems, we might, there are a few cases where we might want to mitigate it. File systems is one thing. We could define on a per file system basis a way to deal with this. For example, saying that in a particular file system as a mount option, we only support times from 1990 to 2100 something. Just by changing the wraparound differently. We have to do the same thing in real-time clocks. So a lot of real-time clocks have a hardware 32-bit register representing the seconds, but they don't care about the absolute value. So we could either have an offset there, or we could change the wraparound time. Like, say that everything that's before 2013 becomes a date in the future. Because we know that there's nobody's going to set, like nobody in their right mind would set the real-time clock to a previous date, because it's not the correct time. Any other questions? Last call. Okay, thank you all for listening.